All right, today we're jumping into a classic lab experiment, synthesizing phenyl benzoate. Now I know that sounds a little complicated, right? But what we're actually looking at is a really clever chemical shortcut, a fundamental technique that's used to create all sorts of things, from plastics to perfumes.
So, here's our game plan. We're going to start with the big picture, the core reaction itself. Then, we'll uncover the key transformation, kind of the secret sauce that makes it all work. After that, we'll walk through the actual synthesis, step by step, see what we ended up with, and finally talk about why this whole process is so important. Okay, so, first things first. What's the big idea here? Well, at its core, this whole experiment is really about a fundamental process that chemists use, like, all the time.
The process is called esterification, and honestly, the easiest way to think about it is like chemical matchmaking. It's pretty simple. We're taking a molecule from the alcohol family and setting it up with a molecule from the acid chloride family. When they get together, they form a totally new compound called an ester.
So who are the players in our little matchmaking story today? On one side, we have phenol. That's our alcohol. And on the other, benzoyl chloride. That's our acid chloride. The goal? Get these two to react and create our target ester, phenyl benzoate.
Okay, but here's the thing. There's a catch. You can't just toss these two chemicals into a flask and hope for the best. It doesn't work that way. We need something to kickstart the whole thing, a little push. And this, right here, is where the real magic happens. So here's the secret. On its own, phenol is what chemists call a weak nucleophile. Basically, it's not very aggressive. You could almost say it's chemically shy. It just doesn't really want to go out and react. But when we add a base, in this case sodium hydroxide, something amazing happens. It transforms into the phenoxide ion. And this new guy, it's a strong nucleophile. It's no longer shy. It's super motivated and ready to react fast. And you know what? This whole clever trick of using a base to power up a reaction, it actually has a name. It's called the Schotten-Baumann reaction. It's a pretty famous method for doing exactly what we're doing here, getting alcohols to react with acid chlorides by making the conditions basic. All right, so we get the why now, right? We know the secret to getting things going. So let's dive into the how. I'm going to walk you through the recipe, step by step, for making our phenyl benzoate.
It's actually a pretty straightforward process. Step 1, we've got to activate that phenol, right? So we add our base to create that super reactive phenoxide ion we talked about. Then step 2, we add the benzoyl chloride, but we do it slowly, drop by drop while shaking the whole time. You gotta keep things moving to make sure they mix well. We do that for about 10 minutes just to be sure the reaction is totally finished. After that, it's all about cleanup. We wash everything with cold water to get rid of any leftovers. And the final step? We filter out our solid product, let it dry, and if we want it super pure, we can recrystallize it with a little ethanol.
Okay, so after all of that shaking and washing, what do we get? What's the payoff? The really cool thing about this particular reaction is that you don't have to wait. The results are pretty much instant. Let's take a look. Seriously, it happens in a flash. The moment that benzoyl chloride hits the mixture, boom, a solid just appears like magic, precipitating right out of the liquid. And that is our phenyl benzoate, forming right before our very eyes. It's the proof that our little chemical matchmaking plan worked perfectly. So, let's look at the official profile for what we made. We got phenyl benzoate. It's a white crystalline solid. And chemically, it's what's known as an aromatic ester. And we made it all using that super efficient Schotten-Baumann reaction.
Okay, so let's wrap up with the big takeaways. Because it's not just about the cool white powder we made. It's also about doing it safely and understanding why this whole method is so darn useful.
First up, safety. And this is non-negotiable. We're dealing with some serious stuff here, like benzoyl chloride. It's corrosive, so you've got to handle it with care. That means no inhaling vapors, and definitely adding it slowly so nothing splashes. And remember those basic alkaline conditions we needed for the reaction to work? Well, keeping it that way is also a key part of keeping the reaction safe and under control. And that right there, that gets to the absolute core of why this reaction is so awesome. It's fast, it's efficient, and you get a really pure product at the end of it, all without needing some crazy complicated lab setup. It's just a really elegant and practical way to build new molecules. So that leaves us with one final thought to chew on. We've just seen a really simple but incredibly powerful way to build something new from scratch. It kind of makes you wonder, doesn't it? Where else out there, maybe in medicine or new materials or even in manufacturing, are these kinds of elegant, simple solutions just hiding in plain sight, waiting for someone to find them?